Guys. So, we're going to get into detail today about how to more specifically describe solutions. We know at this point that a solution is a homogeneous mixture where you have something dissolved in something else. So, the word solubility, it's a little more specific than just like whether something will dissolve or not in water or in another solvent, but it's how much of a solute can be dissolved in a solvent at a particular temperature. So we're going to see in a couple minutes that water or whatever your solvent is, depending on the temperature of it, you either have more space or less space for solute to fit. So you can dissolve more or less stuff in water depending on its temperature. So the word saturated, if you describe a solution as saturated, that means that you're dissolving the maximum amount of solute in the given solvent. So, in other words, the water is full. That means that if you were to try to dissolve any more solute, if you put more sugar or more salt into the water, instead of dissolving, it would just fall to the bottom because there's no more space left. Okay, so typically from the outside, how we tell a solution is saturated is that it has undissolved solute at the bottom. The only reason why that solute would be sitting there would be because the water is already full. Okay, so that's a good thing to know about like what it looks like from the outside. Unsaturated means that we have less than the maximum capacity of the water. So if you did try to put more solute in, it would dissolve because the water has room in it. So let's write that here. More solute will dissolve, which is different from the saturated solution where we would say it would fall to the bottom. Okay, so I want to write here full. Okay, supersaturated is a pretty complicated type of solution as far as making it goes. But basically, you can hold more than the maximum amount of solute. So there's a way to do this where the water has a certain capacity and you force more solute to dissolve. So because this is like a difficult thing to do, these types of solutions are very unstable because the water is not supposed to be holding all of that solute. And any extra solute that you try to add will disturb this very unstable solution, and anything over its maximum capacity will precipitate out. It'll undissolve and turn back into a solid. So extra solute will cause precipitation. Undissolving is not really a word, but that's what it means. Any of that extra stuff will fall out. So there's a very specific way to do this. Make a supersaturated solution, and I'm going to show you that in class the next time I see you. So we'll talk about that. All you need to know now is that it's really holding more than it should, so it's unstable. All right. So as far as like looking at solutions go, it's always easy to tell a saturated solution because it will always have stuff sitting at the bottom. Unsaturated and supersaturated, there's no way to tell them apart by looking at them because everything is dissolved. What you'd have to do is do the extra solute test. If you put in extra solute and it dissolves, you know you had an unsaturated solution. Where if you put in extra solute and everything comes falling out, you know it's supersaturated. Another way to tell what type of solution you have is to look at a solubility curve graph. So in the Regents reference tables, this is table G. And each line on this graph represents a different solute. And it shows you at different temperatures Down here we have the temperature axis. How many grams of each solute can dissolve in 100 grams of water? Okay, so just different substances have different solubilities than each other. On top of that, we're adding temperature to the mix and showing you guys how much more or less can dissolve at a given temperature. So that's important. You guys will be given table G if you need to answer questions regarding it. Okay. So how do we know if a solution is saturated? If you plot a point on this graph and that point is on a line, if it exactly hits the line, we know it's a saturated solution. If your point is under the line, then we know it's an unsaturated solution. And if your point is above the line, then we know it's a supersaturated solution. So let's look at this example. This example is talking about KNO3. So you need to look on table G and you need to find the line that represents KNO3. So that's this big curve right here. You also need to pay attention to the temperature, guys. So this is talking about 60 degrees Celsius. So we want to find 60 degrees Celsius, right? And they're telling us we have 105 grams dissolved of KNO3. So I go to 60 degrees Celsius, I go to 105 grams, and I want to see where my two fingers meet up. And they meet up right here on the KNO3 line. So if I'm on the line, that means that I am saturated. Okay? 80 grams at 60 degrees Celsius is under the KNO3 line. So this solution would be unsaturated. And 120 would be right here. So that would be above the KNO3 line. So that would be my super saturated solution. 100 grams of water should really only hold 105 grams of KNO3. So if we force in an extra 15 grams, that's going to be a supersaturated solution. Okay. All right. So just in general to talk about solubility. Solubility depends on a few factors. The first thing is the nature of the solute. We see all these different lines on this graph. So different solutes have different solubilities. That's just what they are. So an example of a question you might see where you can use table G to answer the question. It says, which substance is most soluble at 50 degrees Celsius? So they're giving me a temperature of 50, and they want to know which substance is the most soluble. So guys, this reference table here, this axis represents solubility. So if you just go to 50 degrees Celsius and see which of these lines is the highest, then you'll know which one is the most soluble. Okay, so I want you guys to give that a try. Go find these 4 lines at 50 degrees Celsius, which one is the highest. Okay, so now that you're back, we have SO2 down here. We have KClO3 right here, that's above it. We have NH4Cl, oh, that's all the way up here. And we have KNO3, that's all the way up here at 50 degrees Celsius. So that's going to be my answer. If the question asked which one was least soluble, you would find the line that's lowest at this temperature. All right. The other thing we can look at, guys, and sometimes table G can help us. If the solid substance is on table G, you can use the curve to help you think about this. So, for example, let's look at KNO3. KNO3 is a solid, and we notice that the line goes up as temperature goes up. So that's true for any solid. As you increase the temperature, you increase solubility. So anytime you want to get more solid to dissolve, you can raise the temperature of the solution. what happens is your water molecules spread out and they create more room and you can fit more stuff inside there. I think about my iced coffee when I do this. If I dump sugar into hot coffee, it's gone, right? I don't have to stir. It's there. It's gone. When I put sugar into my iced coffee, I stir it up, some of it dissolves, but I always end up with like solid sugar sitting here at the bottom. Cold solvent has less room in it, so less sugar, less solute will be able to dissolve. All right. Now, for gases, it's actually the opposite. What we want to do is we want to decrease temperature. And you might be thinking, like, that doesn't make sense because when water is warm, it has more room in it. That's true, but when you think about gas naturally wants to spread out. And if there's an opening at the top of the container, it wants to leave, right? So when we talk about dissolving gas in a liquid, think about your soda, right? You want to keep the bubbles in. So if your water is cold, the water molecules are going to be closer together and it's going to be better for holding that gas in and keeping it down. Okay, if we look up at table G again, HCl, NH3, and SO2. What do you notice is different about those three lines versus everything else on the graph? They're sloping down. They dissolve better in colder temperatures than in warmer temperatures. So we know that because they're going down like that, they're gases. They dissolve better in cold water. Now, the other thing you can do to help a gas dissolve better, and this only works for gases, is you can increase pressure. So guys, that's the same as like keeping a lid on your soda bottle. If your soda bottle has a lid on it, that lid is helping keep those bubbles down. It's helping keep them dissolved. What happens when we open the lid of a seltzer or a soda? All my bubbles come flying out, right? That's because then we've lowered the pressure and now those gas bubbles are able to escape. All right. So if we want them dissolved, that means we don't want to let them escape. Okay. All right. So now a closer look at saturation. So guys, what I want to explain to you here, and we're going to get into like this word dynamic equilibrium more closely in the next unit. But dynamic means changing, while equilibrium means it's staying constant, it's staying the same. So these two words kind of work against each other, but as long as they're both happening at the same time, both changes, then everything actually is able to stay constant. So how do we know if a solution is saturated by looking at it? We kind of talked about that already. So I have some dissolved particles. I'm going to draw them here. Here are my dissolved particles. So let's say this water is only capable of holding 5 particles, right? So anything extra that I add is going to fall to the bottom. So I'm going to color them in so that we can see the difference. So here's the extra particles that I tried to dissolve, and the water was like, nope, I'm full. You're going to sink to the bottom. So what actually happens is, as one of these particles precipitates, or falls to the bottom or undissolves, now the water has room for one more to dissolve. So what's going to happen is I'm still going to have 5 particles dissolved, but one of them is going to be the one that was sitting at the bottom. And now we're still going to have 4 particles sitting at the bottom, but they weren't the same 4 particles that we started with. So we can't actually see this happen. If we look at a glass of water that has salt sitting at the bottom of it, that amount of salt is always going to look the same to us from the outside because it is, but know that inside the particles are actually switching places constantly. So as things are dissolving, things that were dissolved are undissolving, and that change is constantly happening. Dissolving and crystallization are happening at the same rate. Okay, so that's always going on in a saturated solution, which is pretty cool. Okay, so what kind of questions, what kind of other questions are you going to be asked as far as table G goes? It'll get a little bit harder than just what kind of solution is it? Saturated, unsaturated, supersaturated. So let's take a look at example number 1. I dissolve 10 grams of KClO3 in 100 grams of water at 40 degrees Celsius. So let's plot my point first. I'm at 40 degrees Celsius and I dissolve 10 grams. So where is that point compared to my KClO3 line? It's under it, right? So right now I have an unsaturated solution. So now what they're asking is how much more can I dissolve to make a saturated solution? So saturated solution means that I'm hitting the line. So right now I'm at 10, but to get up to the line, I have to get to 15. So how much more can I add? About 5 grams. Okay. And you can do this for any of these lines, guys. If they give you an unsaturated solution, you just want to say, okay, how much more can I add to get up to that line? And this is like an estimate. If you thought the KClO3 line was more at like 16 than 15, and you said you would need to add 6 grams, that would be acceptable. All right, next type of question. How much KClO3 will precipitate out? That means undissolve of a saturated solution at 70 degrees Celsius if I drop the temperature to 10 degrees Celsius. Okay, so 70 degrees Celsius, KClO3. So I'm going to say about 36 grams. So water can hold about 36 grams of KClO3 if the water is 70 degrees Celsius. Now, guys, if I cool the water down, my water molecules are going to get closer together, and all the room that was in that water is going to disappear. It's not going to be able to hold 70 grams of stuff anymore. At 10 degrees Celsius, I'm actually only able to hold about 6 grams of stuff. So they want to know how much stuff is going to fall out. So if I look at the difference again between my two temperatures, I'm going to get about 30 grams of KClO3 precipitating. Okay. This is similar to like when you guys like make iced tea, right? And then you put the iced tea in the refrigerator, or even if you buy iced tea in the store. Sometimes if you look at the bottom, there's some solid stuff sitting there, and that's just probably because the iced tea is very cold. So all the sugar that was dissolved, it couldn't hold it anymore because it got too cold, so it came out. All right, last question, and then I'm going to give you guys some practice on your own. At 40 degrees Celsius, how much KClO3 can dissolve in 50 grams of water? Okay, so guys, this is so important here. This graph is specifically for 100 grams of water. So if the question gives you any other amount of water, you have to adjust your answer appropriately. So first, let's go to 40 degrees Celsius and let's go to KClO3. Okay, so if I have 100 grams of water, I should be able to dissolve about 15 grams of KClO3, right? What if I only have 50 grams of water? If you cut your water in half, you have to cut your grams in half. So instead of putting 15 here, I'd have to put 7.5, right? Cut it in half. What about here? What are they doing to the amount of water here? They're doubling, right? So if I'm doubling my water, I can double my solute. Instead of being able to hold 15, I'm actually able to dissolve 30. All right. So give some of these questions a try, and I will see you guys tomorrow.